Hi, Andrew. You found your
Hey,
way.
how are you all?
Good.
Okay, so this is good. We can go ahead and get started. So let me first start by welcoming everybody. So I will
Do you want to wait one more minute?
share my
Because people are
screen.
rapidly arriving right now.
Sure, we'll wait a few minutes.
Can model the Poisson process of attendee arrivals.
Non-Poisson process.
Okay, what distribution would you use for this point process?
I think the term is point process is a good term for if that would be fine.
Okay.
I once had can I talk? Is it okay?
Yes, of course.
Yeah, no, I once I had to I years ago I was I once had a situation where the data really looked like a random process, like nothing ever does, right? And it was some people who worked at there was a housing development in New York City that had they had an election for, I don't know what it was, their board of directors or something. And some people who were there were concerned that the election wasn't fair. And they had recorded data after it was, I think there were about 6,000 votes, and they recorded data that tallies for the different candidates after 1,000 votes, 2,000 votes, 3,000 votes, 4,000, like that. And they plotted the percentages over time, and they looked suspiciously stable. And so they felt that the votes were rigged. And well, of course, one reason why things are looked suspiciously stable is after the first 1,000, you're averaging the same things over and over again. So the average after 5,000, 4/5 of that is the average after 4,000. So you'd expect a certain stability. But you can then, of course, you can subtract and get the increments. And the increments should look like binomial random variables if everything is independent. But of course, things shouldn't be independent because some people vote in the morning, some people vote in the afternoon, some people vote in the evening. They're different people, right? So there's no way it would be the same. The data were actually consistent with the completely random voting. So there was no, there wasn't under dispersion. So the conjecture had been that there was suspiciously low variation, and there wasn't suspiciously low variation. But I have to admit, I was surprised that there was no more variation than you'd expect by chance alone. That was a rare case of a fairly large data set where there was no apparent pattern. So it can happen.
Well, so we have 100 participants on the call right now, and hopefully more will join us. So let me start by welcoming everybody to the Boston chapter of the American Statistical Association. My name is Olga Vitek. I am the chapter president. I'm really excited that we have so many people joining us today. And in case you're not familiar with the Boston chapter, we are an association who brings together anyone interested in statistics and data science. And it's a regional association specific to Maine, Massachusetts, New Hampshire, Rhode Island, and Vermont. However, you can be anywhere in the world and still join us. You are most welcome. And we try to organize various events, both scientific and social, which would allow us to learn more about important topics of the day and also get to know each other and interact. And so this is our website. And I would like to attract your attention to this tab of upcoming events. So there are quite a few things happening. Of course, the webinar today that we're all very much looking forward to, but there are also other events coming up later on in the year. So here is one event which is focusing on statistical considerations for non-proportional hazards and applications. So this is more of a short course. And there's another event called May Institute on Computation and Statistics for Mass Spectrometry and Proteomics at Northeastern, which focuses on data science for a particular type of biotechnology applications. And there's another short course coming up later on master protocol and drug development. This is targeting primarily people who work in pharmaceutical industry. And of course, later in the fall, there's a New England Isolated Statisticians meeting, which is already being planned in November. So this is for those who are not part of large departments or maybe are in companies where very few statisticians are employed. And this is an event who allows people to find their colleagues, even if they don't have interactions focused on statistics during their daily activities. So please consider joining us, consider becoming a chapter member, and this will allow you to receive the announcements. During the pandemic, we made a choice to offer everything for free and no fee. In the future, occasionally, some events have a membership participation fee, and members of the chapter have substantial discounts. So please consider joining us regardless of where you are located geographically. So this is all I would like to say about the chapter. And so now let me invite Joe Blitzstein, who is a former chapter president, to introduce our speaker today.
Okay.
Thank you so much.
Yeah. Hi, everyone. So it's my pleasure to get to introduce Andrew Gelman, and thank you, Andrew, for joining us tonight. And also thank you to Olga and Wenting. Wenting Cheng is our chapter secretary, and she will be moderating the Q&A. So that for everyone out there, you know, we want this to be as interactive as possible. And so please ask questions throughout on your Zoom controls. You can find a little Q&A button, and you can put questions there throughout the talk, and Wenting will help moderate those. So yeah, thank you all for coming. So Andrew really needs no introduction, and I will try to keep this introduction short because you want to hear from him, not me. He's a professor of statistics and political science at Columbia. You know, I'm not going to try to summarize his 32-page CV for you. I would just say, you know, he's one of the world's most famous Bayesian statisticians and probably has the world's most widely read statistics blog, many of the most influential statistics books and articles out there. So we're really happy to have him here to discuss the most important statistical ideas of the past 50 years. I'll just tell you one quick story about Andrew, because years ago, you know, we were lucky enough at Harvard in my department to get him to teach a course, even though he's at Columbia. And so he agreed somehow to come, you know, commute between New York and Boston every week, which I thought was completely crazy. So he was taking the train every week, you know, from New York to Boston and back to New York. And yeah, I thought that was completely crazy, but it turned out when he did that, he wrote this entire book, Red State, Blue State, Rich State, Poor State, on the train rides. And then he did it again for us, you know, a couple of years later. And for that, he wrote the new edition of Bayesian Data Analysis. This book is often called the Bayesian Bible. So if you haven't seen this book, I certainly recommend checking it out. And I attended both of those courses myself, even though I was, you know, busy with too many things, but I couldn't not attend because it was both so entertaining and so full of insights. I just felt like he could talk for, well, it was a 3-hour course, but it never got boring. It's just story after story after story. And then all the stories have so many insights to them. So really happy to have you here tonight, even if it's virtual. And yeah, go ahead. Thank you, Andrew.
And maybe let me just do a little bit of comments on logistics for the participants. So Andrew would like this to be as interactive as possible. So please use the Q&A button to type your questions. Please don't use chat unless you have comments such as you can't hear or the internet connection dropped. But for the scientific questions to Andrew, please use Q&A, and Wenting and all of us, we will read off the questions as they arise so that you actually have an opportunity to interact with Andrew. So welcome, Andrew. Thank you very much for being here.
Thank you. It's a pleasure to be in Boston in a remote carbon neutral way. I certainly learned a lot of statistics in Boston. And so thank you for the opportunity. I wanted to share a little story with you before talking about the paper. I was contacted the other day. I guess, you know, statisticians, we all get contacted by random people. So I was contacted by somebody who does A/B testing for Wikipedia. I guess they do it probably on a volunteer basis. And they're involved in trying to get people to be more to donate more money to Wikipedia, or to be more likely to give that $3 donation that you sometimes have the opportunity to do. And they contacted me and they said they'd been doing a lot of A/B testing, and they were concerned because they just didn't believe a lot of their results, and they were worried, like, should they do a multiple comparisons correction? They heard that, like, I had some ideas, so what should they do? And I said, well, could you give me an example? And they said, okay, here's an example, just came up the other day. We have there's a little advertisement that comes up every now and then. Would you like to contribute to Wikipedia? And it's a little box with round edges, and we decided trying to make square corners and seeing if it changed the results. And when we did this, it increased, it decreased the pass-through rate by 15%. And we didn't believe, like, 15%, like, what's going on? Like, what, we're not sure, like, what kind of multiple comparisons correction should we make? So you can start as a statistician, you start put these things in boxes in your head, like, experimental design, statistical significance, multiple comparisons. Maybe they should do a hierarchical model. Like, 15% seems like a lot. So I asked if they could share that data, and they're, of course, Wikipedia, they're very open. So this is what you see here in this. You can see the screen share, correct?
Yes.
So there was the control and the treated, and the number of successes, number of trials. So the success rate, I'm not sure if this is people who donated or just people who click through, but it was a 0.5 percentage point under the default and 0.43 percentage points under the alternative. So that is indeed a drop of 15%. You can do, like, there's it's almost 5,000 cases of each, and you can do very simple binomial calculation in R, and you reveals that this is several standard errors away from zero. It's really hard to imagine any kind of multiple comparisons issue that would give you something that many standard errors away from zero. At the same time, it's hard to imagine that putting in square corners. Now, if I wanted to be kind of mean to you, I would have you start coming up with reasons why the square corners could make a difference. But if you stare at this, I just want to give you all 30 seconds to stare at this screen and figure out what's going on here, or what went wrong here.
Please type your comments in Q&A if you have some.
Well, yeah, whatever. I'm not, I'm putting you on the spot. I think you've probably noticed what happened. Many of you have already noticed, I think, which is, look at the number of trials. So it's almost 1 million of each, because Wikipedia have lots of data. But how come this 954,630, this is 950,000, and this is 1,082,000. It's not like, so I said, like, why are there more in the square corners? Like, it's weird. If it was even, you'd understand. If it was 2 to 1 or 10 to 1, you could imagine, but how could this be? And they said, oh, it's supposed to be 50-50. So what went wrong? They said, well, we don't know. Like, something went wrong. So we can't believe this, like, later thing of the 15%, because we don't even know what was going on with the thing. And they thought maybe it was a some problem. They weren't sure what was going on. So then they got back to me a few days later, and they showed me this. Okay, so the yellow, this is time. It's from 4 p.m. to 4 a.m. when they're running the experiment. And the yellow is the control condition, and the blue is the treatment condition. So I don't know what happened, but clearly more people are getting the treatment in the middle of the night, and more people are getting the control in the evening. And I guess people in the middle of the night are less likely to give money. So that seems like what's going on. I guess perhaps I guess if they had included time in the analysis, they wouldn't have found this big difference, but obviously there was some problem with the experiment. So that's just one of these things. Just wanted to share you that story, just to give some insight as to the kind of interaction between theory and practical issues that come up, that somehow, although this ended up being an entirely practical question, a bit of theory was helpful because that binomial distribution gave us a sense that something was going wrong. And of course, like no Bayesian analysis would have revealed that, like because, or any other, like the standard analysis could just conditions on the number of people in each group. You have to kind of go outside a little bit. And that reflects something that I'm not going to talk about today. It's a topic of a different one of our unpublished papers, which is workflow. And we've been thinking a lot about this recently, about the idea. So if I, forgive me, but let me just talk for a moment about workflow. Maybe that's one of the, that's one of the most important ideas currently, even if not in the past 50 years. Workflow is a phrase that's very popular in software engineering, and it's related to this expression in statistics, which I'm sure you've heard, that theoretical statistics is a theory of applied statistics. So the term workflow refers to a sort of introspection in which we try to look at what we do and understand what works and doesn't work. And it's associated with things like checklists. So the workflow of old-fashioned statistics textbooks is a one-step workflow. There's a math problem, and the workflow is solve the math problem. That's it. Optimize, find the moments estimator, the maximum likelihood estimator. I guess there's really two steps of the classical workflow. The first step of the workflow is to solve a math problem. The second step of the workflow is to do some theory and figure out the statistical properties of your solution. Then moving on, somewhere in the 60s and the 70s, people like Tukey and Box talked about a three-step linear workflow, where first you do exploration and you build a model. And the idea was that model building in the hands of modern statisticians, modern model building was an effort itself. It wasn't, the model didn't just come to you, you had to build it. Then step 2 was to fit the model, and then step 3 would be to evaluate it and check the model. When we wrote Bayesian data analysis, we tried to be modern, and we took the 3-step approach and looped it. So we sometimes call it a circle or sometimes a spiral, in the sense that you're gradually moving forward. So you build the model, you fit the model, you check it, then you use that to expand the model, and you go on from there. So that's where we had, like, that was as of about 1995. That was our workflow for many years. Recently, my colleagues and I found ourselves doing a lot of things that weren't in the classic Bayesian data analysis workflow, things that weren't model building, inference, or model checking. So things like simulated data experimentation, things like fitting multiple models to your data and comparing them to each other. Well, that sounds like nothing, fitting multiple models, but can you formalize that idea? Like, think of what you do as an actual statistician doing, like, whether you're writing a research paper or whether you are, working at a pharmaceutical company or whatever you're doing. Sometimes we fit multiple models to data because we want to understand what we're doing better. Like, we want to fit better models. So we start with a simple model and we keep building up until we run out of computing power or understanding or data or whatever it is. Other times we kind of know what we want to do, but we still build up to it. Like, let's suppose you're doing a classical kind of causal inference problem where you're comparing treat and control, and you want to adjust for pre-treatment variables. You should also do the simple difference in means. Even though you know the difference in means are wrong because the treatment and control might be unbalanced in an observational study, you should do the difference in means, and then when you get a different answer, then you can explain, like, you want to explain how they differ. You want to understand that, you want to decompose it. So but this is not part of the official steps of Bayesian data analysis, nor is simulated data experimentation. So we realized that workflow is not just that. So that moved us to a new version of workflow, which is expressed in a recent unpublished workflow paper, which is that Bayesian workflow, and by extension statistical workflow, involves a whole bunch of different tools, which can be roughly categorized in terms of model building, fitting, debugging, exploration, like different things. So that's where we were until recently. But then we had a new idea, which I really like. But I won't tell you that now, because that's not really the topic of today's talk. Let's talk about the most important statistical ideas of the past 50 years, because that's what I promised I'd talk to you about. Some other time you can hear about what I think is the new way of doing workflow. So we wrote this paper. Aki and I wrote, Aki Vetteri is my collaborator. He's a statistician and computer scientist. And I don't really know why I wrote this paper, except I kind of felt somebody had to. The year 2020 had come. 1970 did seem like a kind of pivot point in statistics. A lot of stuff was done in the 1970s. So starting in the early 1970s, we had robust statistics, a lot of work on that, starting with the work of statisticians like Peter Huber, but also econometricians in the late 70s, using some of the most popular methods out there. What else? Counterfactual causal inference. So Don Rubin did his work starting in 1974, and actually some earlier work that he did with Cochrane on matching and regression, the missing data, latent data framework of causal inference, that got started in the 70s. There were wait on the questions. Let me give my spiel first. Okay, so that happened in the 70s too. Of course, there were antecedents to all this. So Tukey wrote about robust statistics back around 1960, and of course, a lot had been done in causal inference and econometrics before the 70s. But the 70s was a time when it became like okay to do some of this stuff. Like robust statistics broke out. Causal inference became something that you could talk about in a formal way. Multi-level modeling, hierarchical modeling, papers by Lindley and Smith and Lindley and Novick, they were around 1970. Then a lot of great stuff got done later in that decade. Bootstrapping, that's from 1970. There was no bootstrap before that, right? Yeah, there's jackknife. There's again, there were antecedents, but the idea that we could kind of bootstrap everything, that we had this like break the glass, here's a solution to any problem, just the idea that we could have a statistical method that would solve any problem. Of course, bootstrapping doesn't solve every problem, but it's not that it solves every problem, it's that it could solve any problem, right? It's like maximum likelihood. It doesn't always work, but you can always try it, right? Like a method, like that's not true for everything, right? Like linear, like if you think like there's like certain computer, like an optimizer, you can fit to anything. Like linear models, you can only fit to linear models, right? So the idea of like, there's a generality to something like bootstrapping. Then we talk about hierarchical models. I already mentioned that. EM algorithm, a lot of computation since then, obviously Gibbs sampling, all sorts of computational ideas. A lot of them really got going in the 70s and 80s. The idea of over-parameterized models. Like, so Good and Gaskins wrote an influential paper back in 1971. Grace Waba did a whole bunch of very important papers in the 1970s. This idea that you can have non-parametrics, meaning infinitely parameterized models. So some of that is just flat out math. Like there's math on things like Dirichlet processes, Gaussian processes. The idea that you can have a model that's implicitly infinite dimensional, even though you don't see it all at once, that's really beautiful. Just a mathematically beautiful idea. There's also some ideas that didn't really work so well, like sieves that were around in that time, but they were kind of responding to similar goals. I mentioned generic, so I mentioned things like Bootstrap, which is a generic inference algorithm. And then I mentioned things like EM, Hamiltonian Monte Carlo, which are generic computational algorithms. Again, algorithms apply to anything. And then ideas in decision analysis. I mentioned robust inference, and finally exploratory data analysis, which really with Tukey's 1977 book really kind of jumped in there. And that's been an area I've been working on a lot. I only cited myself twice in this paper. I tried to be very balanced, and I'm sure that like I didn't succeed, but I tried not to just talk about my own work or my friend's work. Aki and I tried to talk about things that we don't directly do, but have been very important and influential. But I will say that my only papers that I cite are my recent paper on Bayesian workflow and my paper where I tried to, from 2003, where I tried to integrate exploratory data analysis and Bayesian inference, because I think these ideas are connected. So that's kind of one of the themes of our paper, is how these things are connected. So before getting to your questions, I just want to kind of, I already sent you the link to the paper, so you know about that. So rather than talk about that, I just want to talk about why anyone should write a paper like this, like beyond like we get old and so we think about the past, and that's very pleasant. I don't know, like to me, it's just like, I think basically there's a saying, so Bill James has this saying that the alternative to good statistics is not no statistics, it's bad statistics. And there's a generalization of this, which is the alternative to X is not nothing, it's just a bad version of X. Okay, so it's like, why should you fall in love with somebody? Isn't that really stupid to fall in love with somebody? That's not, it's like, you got to, because like you're going to have emotions anyway, and love is probably one of the better emotions to have. Okay, and what about writing a paper about the most important ideas in statistics in the past 50 years? You don't have to write a paper like that. I think a lot of you have better things to do than write papers like this. This is like stuff we do when we retire, et cetera, et cetera. But I would argue that if you don't write this paper, you're writing it in your head anyway. You're thinking about that. What are the most important ideas? We're always thinking about this. So let's try to think about in a useful way, right? Like, let's not, I don't want to write a paper, what were the most cited articles in the last 50 years, right? Who has had the most honors, right? Like I did talk a lot about people in this talk, like people like Tukey and Waba and Efron, who keep coming up over and over again. Of course, the people did the work, but it's not about that. Like, it's not, I didn't rank the 8 ideas. I just put them in somewhat arbitrary order that they came to me. So I think there are ways of reflecting that can be useful, and we're going to be reflecting anyway. And so instead of a ranking, I'd rather try to think this through. So that's my personal motivation in doing this. So now we have a few minutes to talk about some questions.
Sure. This is a question from Mingfei Li, so I will just read it. Thank you very much for the paper. I think it's a good summary and analyze the past is very necessary to go forward. So any more insight about the next new breakthrough statistic ideas?
You should probably ask somebody younger than me about that. I don't, like, what would be the next breakthrough? I guess if I had to say, like, you know, sort of setting aside whatever I do, like, I don't know, there's a kind of incoherence in statistics, not in a bad way. Statistics has always been an incoherent field. Statistics is sort of like a chemistry-like field, and math is like a physics-like field. Like, things don't always seem to fit together. But they're like, on one hand, like, non-parametric, like machine learning is just amazing. Like, every time people try to say machine learning is not all that, they're really actually admitting it is all that, right? It's like if somebody, it's like, oh, come on. Oh yeah, they don't really have self-driving cars. They only work almost good. I mean, come on, like, they're pretty impressive, right? Like, oh yeah, that image classifier can be fooled if you put a dog with a cat mask on. Well, yeah, we'll give it a chance, right? Like, they'll figure these things out. These things are amazing. They have computers that can play ping pong now, right? I can barely play ping pong myself. It's super impressive. So on one hand, we have that, which, like, just seemingly can't be beat and is only going to be better. And it's like, so in that sense, like, classical statistics is John Henry, and, you know, machine learning, like, that's the locomotive. Like, on the other hand, it does seem like classical statistical ideas keep coming up. So we've seen this with coronavirus and all that. People are doing little causal inferences all the time. And, you know, what's the effect of different policies? And as we know, there's no way of avoiding asking these questions. Remember our principle that the alternative to thinking about X well is not thinking about X, it's thinking about X badly, right? So people, like, kind of old-fashioned statistical ideas are seemingly always going to be there. How much, I think a big open question is to what extent do these get integrated? Like one way to integrate this is to take machine learning methods and put them in a Bayesian context and say we're fitting a big ass model and our computations just approximate, but we think of it as Bayesian. We can do the kind of tricks that people like Tamara Broderick or Mike Jordan do to try to get uncertainties. Like basically you take your machine learning inference and you kind of treat it as a posterior, even if it's not. Like that's like, like a lot of things, like you have a dog and you pretend it's house trained until it's not. And then when it's not, you figure out how to deal with it, right? You kind of, that kind of attitude works surprisingly well, and not always, but often. And that's kind of one approach. The other approach is to think of statistics, classical statistics, like classical, I include everything that I do, like regular statistics, model-based statistics, as a kind of last mile thing. That no matter what people do, someone's going to build a self-driving car, but somebody else is going to have to do some inference to figure out like how many people are getting killed by the self-driving cars. And ultimately that's going to be kind of our regular inference, like what I consider Bayesian inference or causal reasoning or whatever. So, but those are kind of two ways of thinking about it, but maybe it's pretty open how things are going to go from there on.
Okay, so I start to see a lot of questions in a queue. And next question is from Hiraki. And this is an interesting question. In the last 50 years, what statistical ideas were bad ones?
Oh, bad ones. I've had some bad ideas. I mean, sometimes, well, like I've had some bad computational ideas. Like I had this idea I called wedge sampling, and the idea was that, well, there's this thing of importance sampling. You sample from the wrong distribution and then you compute the importance weights. Importance sampling is kind of a bad idea. It won't work in high dimensions, but we often still do it, not because we're stupid, but because we have approximations. So like we have a kind of modern way of thinking about importance sampling. Simple idea of importance sampling is you sample from G, but you want samples from F. So you take the importance ratio F over G, and then you get unbiased estimates. That won't work unless it's in general, because if you don't have a good fit, it has infinite variance, and it's not even unbiased because you're doing ratio estimates with your weighted averages. But the kind of more sophisticated way of thinking about its importance sampling is it's a way of getting an approximate intermediate distribution. So importance sampling can be thought of as a kind of poor man's, poor person's, I guess I should say, a kind of poor person's variational inference. So variational inference is more important than you realize, because you think of variational inference as like maybe something that somebody uses to fit models and it's like kind of black magic, or you think of it as if you can't do real Bayes, you do variational inference. Variational inference is kind of the general term for these approximations. In fact, the famous EM algorithm is a special case of variational inference where it's a point distribution that you're estimating. So importance sampling can be thought of as a version of that. So I had this idea, like, okay, so my idea was you approximate a distribution at the mode, and then you get some sort of Gaussian type thing. That's your importance approximation, and it doesn't work so well. But I thought, what if you divide it up into you partition it into, if you take a random draw from a multivariate normal or T or whatever, you partition it into the direction of your draw, which is an n-1 dimensional object, and the distance from the center, which is a one-dimensional object. So it's the angle and the distance. And so the idea of wedge sampling was that you sample the angle and then you do a line search along the ray starting at 0 going out in the angle. That way you can adapt because you can use the local importance ratios along the line. So the idea of wedge sampling was that you could get, like, you get this last dimension, which is the distance, and you can get it right. So I was really excited about it, but like I tried it on some examples and sometimes it worked, but then I tried it on a simple, I did a least squares regression with 105 data points and 100 predictors. So then you get like all but one dimension is Gaussian, but you get a chi-squared 3 for the variance parameter. And I thought, well, that's an example where maybe wedge sampling would work, but it just didn't work at all. So that was a bad idea. I mean, there are a lot of bad ideas. But like, why should I talk about other people's? I'm just trying to think if I had some bad ideas that weren't. I feel like I had some bad ideas that weren't just computational, like bad design ideas. I mean, design is important too. We shouldn't just think of data analysis. Data collection is important. Maybe like, I mean, the biggest idea the biggest bad idea is probably to do small studies and then try to find things. I've done a lot of stuff, I think we all have, where I gathered, like, you gather data, like, hey, let's gather data on 32 patients and let's see what happens, right? And then like everything is very noisy. So I think the biggest error that people make is to not simulate their process before collecting data. Over and over again, we're surprised, like, hey, I got NIH funding. This is supposed to have 80% power. But then I did this and like somehow I didn't get a statistically significant result. What went wrong, right? Or I did, but it's a stupid result. It doesn't make sense. So I think we often just, like, if you want to draw like a chess analogy, we kind of start an attack without thinking about what the other side will do. Now, in this case, the other side is just randomness. It's not, I'm not trying to say be minimax, but we just don't anticipate a move ahead. Like, what will you do? So a few years ago, I was in a project with a collaborator, and before I started, I said, hey, let's not make statistical significance our goal. Let's just start with this. But that was, we rarely do that. So that's, in some sense, you could say, oh, that's not a statistician's idea. That's everybody else. They're stupid people. Except what do statistics books say? We're always like, statistics books have like this much on design and this much on analysis, right? The statistics books are like, oh yeah, here we analyze the data. We win and win and win, right? Like we're always giving examples. If you look at my textbook, example after example where the estimate is like 2.5 standard errors and 0 and the story makes sense. So of course people get that message. So that's what that's probably the bad idea that people keep doing over and over again.
Yes, thank you. The next question is about the computation coming from Claudio. The question is, at what stage can we see that there's too much reliance on computers, using them as black boxes?
Oh, I don't know. I mean, I don't think there's, I mean, there are specific cases where, like, let's say if you're doing a simulation study, sometimes you can do it partially analytically. I mean, I've seen cases where people try to interpret noisy simulation results and they could, like, but I don't, overall, like, I mean, I don't know. I mean, that's like saying, why are you using the damn pocket calculator? How come you're not multiplying numbers in your head anymore? Like, we have the computer, we might as well use it. At some point, I guess there's actual environmental costs. So yeah, I mean, sometimes people leave the computer spinning forever, and like they're like apparently some of these machine learning problems like people are doing, and they really are like literally heating up the planet in a bad way. So I think resources are resources, and so we used to think like wall time was the most important resource, but it's really just, heat is there. So, but that's like, in general, that's like similar, like you shouldn't get data that you don't need. That's a waste. So don't keep your computer running overnight if you don't need it. That's actually a workflow thing, because people get in the habit, like they run the iterative algorithm, it doesn't converge, and they run it longer. But usually when the iterative algorithm isn't converging, that's because there's a problem with your model, and you should like that's not like the solution. So, but the computer isn't the problem, but it doesn't mean the computer will always solve your problem.
Okay. And do you want to go on with more questions, or do you want to continue?
Only more questions. I see in the Q&A. So Nicholas had a question. Nick said about the implications for what we should be teaching. I'll tell you something. I used to teach intro stat every year. And then 20 years ago, I stopped teaching it because I lost I had a crisis of confidence. I did not like what I was teaching. All those p-values and all that. Like, I don't like teaching it even when you teach it in a reasonable way. Like, I still don't like, it's like, I don't want, like, you know, like when it comes to like traditional statistics, like I don't believe any of this stuff. And so I just want to go like full out atheist on it. I don't want to go Unitarian, you know, I don't want to be out there like, oh, well, here's a reasonable way of interpreting the p-value. Like, yeah, here's what you should compute. Like, yeah, actually they talk about one-side tests and two-side tests. Don't worry about the two-sided one-side test. Just do a two-sided test. It's kind of the same as a confidence interval. Here's how to interpret this. Like, I'm really like kind of like becoming Lindley-esque in my old age. And I just can't, I just couldn't do it anymore. And fortunately, like they didn't make me do it. And like, so I just think, yeah, I mean, it's easy for me to say because I haven't done it, but like teaching, yeah, blow it up, you know, start over. I'm not quite sure how. I've been kind of gradually. Regression in Other Stories is a more elementary book than anything we've written before. So we're kind of trying to back into. Ultimately, I'd like to write the high school level textbook too. So yeah, I do think these have huge implications for teaching. I don't know what the implications are exactly. And then I see the Mark asked, what ideas do I think should have been promising but didn't get pursued appropriately? Like, I don't know. I mean, are there ideas like there are things that we're doing now that maybe could have been done earlier, like just because like people didn't think of it. Like, of course, a lot of exploratory data analysis could have been done 100 years earlier. You know, I was a physics student before I did statistics, and nobody needed to teach me about exploratory data analysis because physicists just graph everything all the time. But for some reason, it wasn't so much part of the statistical workflow. So I guess there's probably like almost anything could have been done earlier. And, but I don't really know, like, yeah, it's hard for me to say like, oh, this was this great idea that came out in 1972 and then nobody followed up. Like, why didn't they follow it up? Like, usually you can understand why people didn't follow things up.
Maybe it's also related to the limitation of the access to computers. Like in your paper, you said the data exploratory analysis in the past cannot be done because we don't have the access to laptops.
Yeah. Oh, sure. I think computing is a lot of it. It's not the whole thing. But a lot of it is just kind of cultural. Like you have to, like, we have to get used to certain methods. I mean, if you look at all, like sometimes things go backward. Like if you look at all that horrible regression discontinuity stuff that the applied econometricians are doing, like that. I mean, it's not all horrible. We have some regression discontinuity analysis in our book. You know, it's fine. Like Jennifer didn't have to twist my arm. Like I like it sometimes, but like there's sometimes things get worse. Like people start to believe a method can do stuff it can't really do. So there's a kind of cultural learning we have to do. I mean, just as a society, right? Like just think like 80 years ago, like people believed in communism and Freudian psychiatry and stuff like that, things that like everybody laughs at now. It's just there are things like ideas that are out there that somehow people have to work their way through. I still have big arguments with my friends at Stanford, like people like Rob Tipsirani. I mean, I don't mean ironically like my friends, like they are my friends. Like I really think they do great work. And like, I think that if I had never been born, statistics would be pretty much how it is. And if Rob Tipsirani had never been born, statistics would be a lot worse. Like I think he's great, and I think his methods are great, even though I don't use them. Like you just like you use what you use. But I feel like the idea of he and his collaborators, what they think are the foundations of statistics are things like coverage of confidence intervals. I don't care about that stuff. Like it's kind of weird, like, but I don't, and I don't. It's not like they're wrong. Like that's what motivates them. But like I just feel like that's one of these ideas like communism that people are eventually not going to have anymore. And but we do cultural learning, and that's not like that's happening within each of us, but it's also happening to us as a society. Like we are like a big team, and we can't you can't pull yourself away from that. Like we're all just like, and you see this like also I just want to push against like this like idea of worshiping like individual humans. Like I just did that, like I said how great Tip Girani is, and he's like been in the right place at the right time, and he's wonderful. But I'll also say, and I'm sure you've experienced this, like I work on applied projects with people all the time, and these are people who've maybe never published a paper in their life, or certainly never developed a new method, but like they'll just be like completely on point on what they're doing. Like they'll be like, this, you know, I didn't see that. Like they're right there. Like it's so those of us who are fortunate enough to develop methods that are used for by others, we really have to think about this idea, like the amazing distributed knowledge that people have. Like how can we help society, the academic, scientific society move forward, and while making use of individuals. And I'm really kind of down on the paradigm of textbook paradigm of statistics, which is that like there's something you want to know the answer to. It's like really weird, like doing an experiment, a statistical experiment. I mean, this is kind of off topic, but like whatever, right? There's something that like you want to know, it's really important. Like we want to cure a disease, or we want to figure out like the impact of some policy, or we want to elect a candidate, or whatever it is, like something important, right? And what's the paradigm, the statistics textbook paradigm for solving an important problem? Okay, it's 3 steps. The first step is somebody figures out the solution to the problem. I don't know who, somebody figures it out. Like that's a black box, right? The second step is then an experiment is designed, and data are collected, and a statistical analysis is performed, and a certain result. Well, I don't want to bang on statistical significance. Maybe the posterior distribution looks very good, whatever it is. There's an inference, and the inference is like, yes, we figured it out. And then step 3 is to just sort of, you know, relax and you know, take a victory lap. Those are the 3 steps, right? But like, isn't that weird? The most important step is hidden. It's how, oh, that's not statistics' job, right? Statistics' job is not to figure out what to do. It's just how to evaluate. Well, that's like kind of doesn't seem to work that way in real life. Like when you actually talk to people, these ideas don't fully form, just like whatever that Greek myth Phil came fully formed out of somebody's body part, or whatever it was. Like that doesn't happen, right? Like it's not, so like we're like not modeling the most important part. And it's like when you think of like policy analysis, like what's the right policy for coronavirus? Policy is just people doing stuff, right? I feel like we should be like empowering people. Like statistics should not be about some genius who inside a black box coming up with a method that we test, and then we tell everybody they have to do it, right? Like if we have a good medical procedure or a good education procedure, this should be something that individual teachers or doctors and nurses should be able to like adapt on their own, because they're going to be adapting anyway. Remember the principle, people are going to be doing it anyway, so let's try to do it right. So like, why can't we, like, why can't statistics be like that? Why can't it be like people adapting? Like, why can't the people like on the street or in the warehouse or in the classroom or whatever be using their creativity? And can statistics help them, like, which is a way of helping us? Because that's all we are. We're just people in the fulfillment center of academia, right? Like, yeah. It's like really just ranting at this point. I'm sorry. Other questions?
Yeah, this is a question about the workflow. And so the question is, can you illustrate your ideas within the statistical Bayesian workflow?
Oh, yeah, you can read our workflow paper, but I have new ideas that aren't in the paper yet. So we'll have to wait till the next edition. We sent it, we had this paper and it was like 1,000 pages long. You know, what happened was we had this idea of writing a book like Bayesian, like a Stan book. It was a Bayesian workflow in Stan, and it was just not getting written. It was like not going anywhere. So I just decided to write an article. So I wrote an article and I CC'd like 12 people and said, let's write this article. And then people were really annoyed, like, oh, this article has all these problems. It was a total stone soup thing. Like every time someone said this article sucks because it's missing this, I added it, right? And so then it was this nice article and it was like 75 pages long, which means it's like half of a book. So that got us most of our book. So we're working on that book. Then we sent the article to this journal, Statistics Surveys, which publishes really long articles. And then they're like, your article's a little long, you know, maybe you could cut it. So we're revising it. But then in revising it, it's been very useful because it's given us a chance to think about this stuff some more. So now I have these really great ideas on workflow I really, really like. So I'm really excited about that, but I won't tell you about it now. Right? It's not today's topic, but I just wanted to share my excitement about it.
Yeah, and the next question is about impacts. So the question is, then Leonard was named as the recipient of the International Prize in Statistics for her random effects paper. Any thoughts on that?
Oh yeah, well that's great. I mean that. So this fits into our paper on the most important ideas. I mean, it's not a. It's so in this case, it's about multi-level models, which I think are important. I think they could definitely give the next 8 awards to the 8 topics in this thing. So it's multi-level models, but also it was also related to generic computing algorithms, because like that's this idea, like the EM algorithm as an algorithm, any individual case of the EM algorithm already existed. What was important for that paper was the idea of saying this is a method that you could apply to any problem. And it took a while before we went from EM algorithm to variational inference, and we're still working on it. So it started out as a set of analytical tools. But I think if you think about it as this precursor to, and also it's related to this idea that everything's a latent variable. We had an interesting problem a few years ago in pharmacometrics. I was working with some colleagues at Novartis, and we had data on our drug, and then there was a competitor's drug. The competitor's drug, we didn't have the raw data, but we had averages, because you actually have to report the averages. Like certain things have to be shared. So I think they had 900 patients, which means the straight kind of EM type approach would be that you would have 900 latent variables, actually more than 900, because the model has like 6 parameters and they vary by person. So you'd need to have 6 times 900 latent parameters. That would make it too slow. So we came up with a kind of quasi-analytic approximation that we programmed up. We wrote a paper on it. But the point is that, like, yeah, like this idea, I think what we did in that paper was kind of the child or the grandchild or the great grandchild of what Nan and other people did in the 1970s. And so that was really was a very important decade in that sense. And I don't say that just because that was the decade that I grew up.
The next question is about model complexity. So the question is, as you mentioned, statistical and especially machine learning models are growing increasingly complex. What are your thoughts and advice on still using models to gain insight even when they are large?
I think it's very important. I'm very excited about this area. And this is something that Tamara and her colleagues have been working on, Ryan Giordano and others. The general idea is that, like, so there's a term, exploratory model analysis. And maybe the most general way of saying it is differentiating your inferences with respect to your inputs. So that includes things like influence analysis It includes things like leave one out cross-validation. When we do leave one out cross-validation, we tend to think of the total prediction error, like those famous those tables where you have the tables of numbers and whichever wins is each column is in bold, those machine learning tables. But I'm not talking about that. I'm talking about doing leave one out cross-validation as a way of looking at the fit of individual data points and understanding which data points are the most influential. There's this infinitesimal jackknife idea. We have a term called the topology of models. So I talked about this earlier, that we fit multiple models and Winston Churchill once said, or was said to have said, the truth is so valuable it must be protected by a bodyguard of lies. That was in World War II, or maybe one of his later re-election campaigns. I'm not quite sure which, but in the in our case, like I have this saying that if there is a model I want to fit, even if I knew it was the correct model, I would still want to fit a simpler model to understand what I got from the complexity. And I'd still want to fit a more complicated model just to show that I didn't need it, right? And so it's like this idea of understanding models by comparing them to other models is something we do all the time, but it's not in any of our theory. It's not in any of our textbooks except like something we do. But we can do better. That used to be that way with graphs. Statistical graphics used to be like just something that people did, but it wasn't like official part of statistics, and now it is. So I think this kind of thing could be part of it too. I think there's a phrase, interpretable AI or something. It's like fits in with that too. I think this is a very important area, the next big area.
And there's still a question about computing. The question is, how do you think computing impacted open these ideas?
I mean, I wrote about that in the article, so you can read it. It's like section 2.2. Oh,
Okay.
there's a question in the chat. I have to answer this one. Your paper mentions 2 books by George Box, but I don't mention his book with Jenkins on time series analysis. It has been super important. I don't know. I think we said something in the book about this. I mean, of course, like there's a limited number of citations I can give to any person. I didn't want to cite Box too many times because I kind of already agree with him. Like, so I wanted to be sort of bend over backwards, not to like cite like a million links to like the, heroes of Bayesianism. We could have mentioned it. I think that there are a lot of specific models that have been important. And we did, because I think at one point I did allude to, yeah, I said specific models. So I mentioned hazard regression, generalized linear models, spatial autoregression, structural equation models, latent classification, Gaussian processes, and deep learning. I did not mention spectral time series analysis. I did not mention autoregressive time series models. I agree they're important too. I mean, all I can say is there's just like a lot of, I didn't mention item response models. They're super important in political science and they're important in psychometrics. I agree, like there is a kind of overflowing basket, multi-compartment models in pharmacology. There's a kind of overflowing basket of particular developments that have been very important. I don't see, like I wouldn't say that any of them is like a unifying concept or singly like as important as any of these things are. I didn't put it as kind of one of the 8 most important ideas, but like all of these ideas work with these approaches.
Another question is about a meta-analysis. The question is, what do you think about meta-analysis?
Oh yeah, it's great. I guess I'm with Keith O'Rourke that ideally you should do meta-analysis using the raw data. We don't always have the raw data, but yeah, better. I think that I'm not a big fan of trying to do meta-analysis on published data and try to hopefully correct for the biases. I just feel like it's published results are so selected, like with rare exceptions, like there are certain fields where they report everything, like certain fields of biomedicine, but like, so I think meta-analysis is really important. It's in chapter 5 of Bayesian data analysis. It can go wrong, you know, garbage in, garbage out, all that. But like it's sense getting back to our theory, our big theme, you know what I'm going to say? Everybody does meta-analysis. So if you don't do it, if you don't try to do it right, you're just going to be doing it wrong.
The next question is, can you talk a little bit about how reproducibility and transparency may fit into the workflow you talk about?
Yeah, it's super important, and I think like in terms of in our 50 years paper, I did actually cite 1 or 2 papers on the reproducibility revolution because I think it's kind of been an important idea. I somehow didn't think it was one of the most important statistical ideas on its own, but it's been like important in terms of workflow. Yeah, I think pre-registration, like I don't feel pre-registration's a little bit like random sampling, like even if like a little bit is still better than nothing. So like if you can't, our surveys that we do aren't really random samples of the population or voters or anything like that. Like we get people who answer the phone or who respond to our email questions, but we still try our best. Like we understand that, like, although they're not random samples, we try to get representative samples. We try to cast the net wide. We try to adjust the sample of the population. I think that's similar to when we do our analyses, that even if we don't pre-register, I think it is good to think about what you do before you do it, more than we've done before. In my own career, I've moved more and more towards doing more of that. I think that's just it's the right attitude. Like, I don't think we always have to pre-register, but pre-registration is the standard. In the same way as we don't have to do random samples, and often we can't, but at least we feel bad when we can't do that. We should feel a little bad when we haven't pre-registered things. And of course, pre-registration doesn't mean that you can't do whatever you want later. It just means you're setting out a plan. I mean, that's another thing that they say in chess, is that your plans don't always work, but if you don't have a plan, you'll surely lose.
So Andrew, do we still want to keep going on with the questions, or
Well, I'm speaking elsewhere at 7:10, so I guess we have 7 more minutes. I made a mistake. I agreed to talk on the same paper. Can you believe it? Like, I just didn't think it through because of the time zones. Like, they said theirs was at 4, and actually 4 is 7 for them. It's like the Earth is spinning, and you know, just like the song, like when it seems like the sun is going down, it's really the world spinning. And I hadn't thought that through. Yeah. So sure.
You take one more and then get a 5-minute break.
Yeah.
The last question is, which areas of mathematics do you think will have a chance to play a bigger role in statistics going forward?
Oh, I don't know. I mean, math is good, but I guess programming has become more and more important. So certainly math is still important, like, but I think relatively speaking, I think if like you can't do any math, but you're a really great programmer, you're probably more likely to become a good statistician than if you can't program, but you're really good at math. Like, I guess, I don't know, like it's a different kind of thing. I guess programming is easier to learn. Like you can learn, but I guess it's all these things. It's hard for me to compare. It's hard for me to know. Like, I think you can learn and you can become better at math, and you can become better at programming, and like people should do both, I guess.
Okay, so we'll let you go and have a 5-minute break, but thank you so much for the great discussion and questions, everyone, and all the food for thought from Andrew. So yeah.
Thank you very much.
Okay, that was a lot of fun. And I hope it's helpful to people. Have a good evening, everybody.
Thank
Thanks.
you. And I hope that the participants will be joining us in the future events as well. So please stay tuned and follow the newsletter of the chapter and also the events page on the chapter website.
Okay, bye.
Thanks. Bye.
Thank you,
Thank
Andrew.
you, everybody. Bye-bye.
Good evening. Bye-bye.
Bye.